Hello everybody. I will talk about first result of nuGeN experiment on coherent elastic neutrino scattering. So first I would like to very shortly speak about coherent elastic neutrino scattering. I will not speak a lot because there will be a lot of talks devoted to this topic with much more detailed. So I would just like to mention, so this process has not been yet observed for reactor neutrinos, and the observation of such process, it will be important test of standard model, but also it will be interesting to search for non-standard neutrino interactions, trial neutrinos, and other investigations. So but it's quite challenging to find such kind of process because the recall energy of the nuclei is very low and less than few keV, and often only a small part of the recall energy can be detected due to the quenching. That's why it's not easy to find such kind of process. So our experimental site is located at a power reactor at Kalinin Nuclear Power Plant. It's on a halfway from St. Petersburg to Moscow. You can see on the map its location. So, and here is a scheme of power reactor. So it's a power reactor, that's why it's not experimental one. So it's worked typically in a regime of 1.5 years working, and after that 2 months it is stopped. So that's why we do not decide the schedule, of course. So, but we have very nice location in this building. So our nuGeN spectrometer is constructed at the distance only 10 meters from the center of the powerful 3.1 gigawatt reactor core. And that's give us a possibility to operate an enormous antineutrino flux of more than 5×10 to the 30 neutrino per centimeter per second. Moreover, the reactor surrounding give us a very good shielding against cosmic radiation. Our burden is about 50 meter water equivalent. And that is also very important for us as well. And in principle, so if we compare different reactor sites for the similar experiment looking for sevens, we can see so it's one of the best places because it has huge neutrino flux, one of the best, and also it has a very good overburden. To detect signal from neutrino scattering, we use high purity germanium detector produced by Canberra. It's special low threshold, low background, high purity germanium detector. The detectors are cooled down by electric or nitrogen types of cooling. So we have in total 4 detectors with masses of 1 to 1.5 kilogram. First, we perform a test, a GNR of this detector. So test of first detector showed us very good energy detector performance. So energy resolution was 78 EV and stable performance. So this gives us possibility to acquire signal below 250 EV with trigger efficiency of about 70%. So as you can see here on a plot on the right, on the bottom. So also on the top you can see picture spectra taken with pulse generator of with energy of 260 EV. So to suppress background coming from the different surrounding, so we use the following scheme of shielding. So germanium detector are surrounded by 3D clean printed nylon to displace radon After that, we have a layer of oxygen-free copper, 10 centimeters layer. After that, we have borated polyethylene and 10 centimeters lead, and another layer of borated polyethylene, and active muon vita to suppress background coming from the cosmic radiation. So we also put nitrogen air inside in order to further suppress radon background. The detector is located on anti-vibration system that allows us to suppress microphonics noise. A special lifting mechanism has been installed in order to move spectrometers towards to the reactor core and change neutrino flux through the detector. So such kind of device also, of course, to help us to suppress systematic errors connected with the changes of the background while the reactor on and off, because we can compare spectra on the different distances. So current data that I will talk later was taken under one position here at 11.8 meter from the reactor core. And later we are going to change this distance. So you can see here some photo from the installations. So put shielding and so we put first detector with a mass of 1.5 kilogram and install it. So 3 others were sent to Medion for reparation after unsuccessful general tests. So here is another photo from the installation. So you can see here that we put nitrogen flushing here inside the shielding. So we use anti-vibration platform to suppress microphonic noise. So air conditioners we have in this room that provides, it's very, very important to provide stable temperature condition, better than 2 degrees. And we get experimental resolution with this detector is about 100 eV full width at hub maximum. So all detectors are equipped with the reset preamplifier. A typical rate of reset is about 5 Hertz. So, and special inhibit signal for sure we have to indicate the time when the reset happened. So the signal are shaped after that with amplifier and processed with a real-time PDC. So here is a simplified scheme of measurement. So signal from high purity germanium detectors goes to preamplifier, and after that it's split by the 2 channel, and we process it with the 2 different amplifiers and average signal. But also we compare this signal with amplifier with a different shaping time in order to suppress signal coming from the noise. Also here we record inhibit signal and signal from muon vita in order to suppress cosmic background. We use pulse generator to calibrate this signal as well. After that we check stability, and after that we record everything and perform offline analysis and whatnot. So of course, time cuts allows us to suppress signals generated by reset and other artificial signals. So different shaping time of preamplifiers are used to suppress noise signal with help of graphical cuts. You can see here that physical events are located on the diagonal, and they have the same practically energy. We reconstruct it with the different preamplifiers and shaping time, but noise signal are located somewhere else. So to perform calibration, we use a cosmogenic line from germanium and pulse generator. And we checked our calibration pulse generator with help of 1.3 cosmogenic line of germanium. So here you can see on the picture that our calibration works well. So data taking shows very good stability of peak position during all measurement time. So on a picture below, you can see the position of 10.37 keV peak. And to calibrate high energy part of the spectrum, we use welding rods that contain thorium. And of course, we can check our data with high energy part of the spectrum as well. So we performed data taking with the end of last year. And first, so the detector was stopped in April. So basically we have about 71 days of measurement before detector stoppage. After that, with detector off, we have 33 days. And after that, we have some measurement after. And we continue data taking now as well. So here you can see on a plot the energy spectrum that we obtained when the reactor was on. So black dot shows us the data taken in such kind of condition. So the red line is calculation, is expected contribution from sevens. And blue dots is ratio of expectation to the data. So here we do not apply all the cats, but expecting contribution of the signal from 7 to energy region is in this energy region is more than 20%. So, and what we get if the reactor is off. So, as you can see here, so we do not perform any normalization of the spectrum. So it's just like it is. So, and we do not apply any normalization. So, and you can see that background indexes and the shape of the spectra are identical practically in case of reactor on and off. So this is quite important, that give us the confidence that the background do not change here. And if we subtract one spectrum by another, we got following spectrum. And when the reactor is on, we get a count rate of 2.47 counts per kilogram day. When the reactor is off, we got 2.42 counts per kilogram day. So this give us a confident interval of 0 to 0.47 counts per kilogram day on the 90% confidence level. But I would just to mention that here is only statistical error taken into account. With systematical error, it will be a little bit wider. The expected rate of the events from sevens is 0.46 counts per kilogram day. So, but I just would like to mention that this value is not fully known due to uncertainties of quenching and high energy and neutrino spectra from the reactor. So it has some uncertainty. So at the moment, there is no tension visible so far. And in a conclusion, I would like to say that measurement with nuGeN spectrometer with the first detector at nuclear power plant has been started. So first results showed that achieve background level allows us to search for sevens at KNPP. So far, no significant difference between regime with reactor on and off has been observed. More optimization of the analysis and new detector are ongoing. So we already tested lifting mechanism, and it will be used soon to reduce distance to the reactor core. And And so new results with more statistic and optimized measurement mode are expected soon. Thank you very much.